Good afternoon, everybody, and welcome to what is effectively the final live stream for this course for the year, or for the semester, I guess you could say. So we're going to talk about algorithms today and how we can calculate the complexity of algorithms and do various other things like that. But before we get there, since we are so close to the end of the semester, I'd just like to talk briefly about kind of the plans going forward. So this is the final live stream of the semester, in the final module of the semester. The only thing that you have remaining after this week is your final project. So what I've decided to do is next week I'll have extended office hours on, I believe, probably Tuesday and Thursday, the days when we would normally do these live streams. And during these extended office hours, you can pop in virtually or, in person if you'd like, to ask for help, ask questions, whatever you need in regard to your final projects. So I'll post the times on Friday with your weekend reminders. And this will be for all of my classes, all of these extended times. So, could be anybody popping in, asking questions about anything. But I just want to make sure that there's ample time and ample opportunity for you all to ask questions of me while you are working on your final projects. So with that being said, I'd like to move into just, well, you know what? Before we start talking about algorithms, I just want to take a moment and thank you all for watching the live streams this semester. I hope something of it was valuable. I hope that you got something out of watching the live streams and getting the information there. I hope it was helpful. I hope it helped facilitate and make things easier in the modules. The way that I kind of look at it is like this time during the live streams, that's kind of class time. And then everything in the modules, that's kind of your textbook. And so you can take the two and kind of put them together and get a complete class. And that's kind of the way I handle it. So I hope you all were able to get some valuable information and learn some things from these live streams this semester. So now let's talk about algorithms, shall we? So I think the first thing that we need to do before we get into the analysis of algorithms and how efficient an algorithm is just remind ourselves what our working definition of algorithm is. Because essentially our working definition of algorithm is just the sequence of steps that it takes to solve a problem. Right? If you'll remember way back in the beginning of the semester, right? And this is why I kind of do this, like it bookends the beginning and the end. We talked about what an algorithm is to try to demystify the term algorithm. And we just said, well, it's just a sequence of steps that specifies how to solve a problem. And that could be mathematically, right? Like that could be an equation, or that could just be a series of actions. Way back at the beginning of the semester, we related it to the idea of like instructions to put together a piece of furniture or something like that. It's this series of instructions that goes sequentially to solve a problem. And we look at computer science in general as the science of algorithms, the science of this sequential problem solving, specifically using computers. And so one of the interesting things here, right, is that as we're getting started, and it's kind of the way that I've been all semester, as we're getting started, as we start our learning journey, essentially what we're doing is we're focusing on that end goal. Right? Like I've told you all semester, if you make me some code that works, if it solves the problem, you've done it. Congratulations. If it works, I'm happy. That might be a phrase that you hear among a lot of programming teachers and in a lot of, junior programming offices. in the career. You know, in careers, you hear the phrase, if it works, I'm happy. And for the majority of the problems that we've been solving this semester, the majority of the programs that we've been writing, complexity isn't really that big of an issue. Right? When we talk about complexity and efficiency, it hasn't really been that big of an issue. Everything that we've done has been relatively small, solved relatively small problems with relatively small programs. And so how efficient that program is doesn't really matter, right? And that's kind of the way that I think it should be when you're learning, right? Like you're trying to figure out data structures and you're trying to figure out conditionals and all this other stuff, and try to add into it, making things as efficient as possible, becomes its own sort of bear, because there are so many different ways to solve a problem. So when you're starting to look at efficiency, you're not just looking at one way to solve a problem, but you're starting to look at 2, 3, 4, 5 different ways to solve a problem and finding the one that's most efficient. And a lot of times we'll talk about this in terms of refactoring, right? Solve the problem and then refactor to make it more efficient. Make it work first and then make it better. Right? And so this gets into our concept of algorithm efficiency. So when we ask ourselves what makes an algorithm efficient, we can essentially look at 4 different things. Time usage, or CPU usage, memory usage, disk usage, and network usage. So when we're looking at what makes a program efficient, we can look at these 4 things: CPU, memory, disk, and network. Well, what do all of those things have in common? The things that make our program perform well, that make our program efficient, CPU, memory, disk, and network, are all hardware components or physical components, none of which we really have direct control over as programmers. These performance efficiency elements are going to be widely dependent based on your user. Each user is probably going to have a different CPU. Each user is probably going to have a different amount of volatile memory. Each user is probably going to have a different amount of non-volatile memory. And each user is probably going to have a different speed of internet. And so when we talk about efficiency, we're looking less at what we would call performance. These 4 things contribute to performance. We're looking more at the idea of complexity. So let's break that down a little bit more. What is performance and what is complexity? So performance is dependent. How much time, how much memory, how much disk is actually used when a program is run. And this is going to depend on the machine or the compiler or some other thing. It also depends on the code, right? Like we can write code that is more efficient for performance. But the way that we do that is we write code with complexity in mind. We write this code with this sort of complexity in mind, and this sort of complexity is about the resource requirements of a program that we're running. As the algorithm scales, as these steps that we're using to solve a problem are used for bigger and bigger and bigger problems, what happens with the program? Our problems get bigger, and in turn they get more complex. Now we can see here that our complexity impacts our performance, right? But our performance doesn't impact our complexity. Complexity is completely programmatic. Performance is dependent on other factors. But when your complexity is high, that's going to have an exponential impact on your performance as our problems get bigger. Because what's going to happen is, we're going to start with a small problem. It's probably going to be able to run handily with the processor, with the memory, with the disk at hand. But as that problem scales, it's going to put more of a grind on performance because more resources are needed to solve that problem. So a poorly spec'd computer can run a low complexity program in a certain amount of time, and that same computer takes more time to run a high complexity program, nothing else being changed, just the amount of complexity in the program. And let's talk about how long it takes for an algorithm to execute. And we actually have a series of calculations. We call this big O notation. When we calculate our how long it takes for an algorithm to execute. Right, and we'll head over to a REPL and we'll do a little example here in a moment and we'll break it down. But when it comes to this sort of calculation, what we're essentially doing is we're looking at the number of basic operations that a program performs. So the time required by some kind of function or some kind of feature is going to be proportional to the number of basic operations that it performs. So as we look at calculating big O, we call it, so to calculate big O, you can go through each line of code and look at each operation and establish what your O number is based on the operations that are present in your program. So when we're talking about operations, we're talking about basic things. We're talking about variable assignment. We're talking about arithmetic operations. We're talking about testing. We're talking about reading. We're talking about writing. Any sort of test. Like when we say test here, we're talking about like conditionals. Essentially any action that needs to be done adds complexity. And so one of the first things that we want to do when we're approaching the complexity of our algorithm is we want to assume the worst. A worst case scenario. So when we're doing any kind of calculations for complexity, big O or what have you, we're always going to think about the worst possible case. What is the maximum number of operations that might be performed for a given problem size? So we have an example here of inserting an element into a list. We have to move the current element and all of the other elements that come after it to one place to the right in our list. So if we have a list of 100 items, right, and then we want to append an item to the end of that list, well, we're going to move every item in that list to be able to stick that item where we want to put it. Or in this case, what we're talking about is we're talking about sorting. So, like if we were to loop over our list and look for an item or move items, it could be the first item, right? Or it could be the last item. And so if we're not sure how many operations it's going to take, we call that an n number of operations. Right, and that's in our big O notation. So in our big O notation, this is an expression of complexity. We have essentially different types of complexities in big O notation that we could represent this as. And so whenever we're writing big O notation, we write it with a big O. A big O. And then in parentheses, we have our number of operations. So if we have something with an undetermined amount of operations, say if your user is able to add more and more and more things to a list, we say that that is ON. If that's looped through 5 times or so, that's O5N. 5 times N. So for each different operation, like we might have 4, like let's say we have 4 variables that have been assigned, and then we're going to loop through an unknown length list 5 times. Well, that's going to be O4 for our variables plus 5N for the number of times that we loop through our list. And this gets a little tricky, right? It all depends on how many statements that we use. It's going to make stuff harder or easier. All right, so let's just take a little sample itty bitty piece of code, and let's break it down and talk about how we can calculate the complexity of it. So in order to do that, I'm going to write myself a little piece of code. Let me find my REPL here that I can write it in. And we're going to just write a really simple piece of code. So we'll start with our shebang, hash bang slash usr slash bin slash env python 3. And I'm just going to write a little function here that will serve to just add 2 numbers together. Right, so we'll just write a little function, def add. We'll use num1 and num2 as arguments. And we'll just have a variable called total and set that equal to num1 plus num2. And then we will return our total. I was doing Java earlier today. Sorry about the semicolons. And so now let's put this behind our main gate and let's just run the little code so we see it, right? So this is if name print add 2 comma 4. Right, so 2 becomes num1, 4 becomes num2, and we print out the result of that, and we get my REPL must have frozen here. Let me refresh it. There we are. So we run that and we get 6 really quick, right? Like it gave me the 6 in my output window, incredibly quickly. So this is pretty simple, right? Like we're just adding two numbers together. But let's kind of break this down into each operation so that we can kind of get a better understanding of what we're looking at. And when we break this down and evaluate each operation, what we see here is we see 4 different operations. Right? We see the lookup of our variable num1. So in this case, num1 becomes 2. We have that lookup operation there. The lookup of num2, which becomes 4. So that you go grab that 4 and put it in the num2 spot. Adding the numbers together and then returning the total. And so in this case, what we have here is we have 4 very simple operations. And each one of these operations just occur once in our program. Right? So we can look at each of these operations as O1. Right? So looking up num1, that's an O1. Because you look that up one time and then you put that into memory. Looking up O2, or looking up num2, that's also an O1. You look it up one time, you put it into memory. The calculation, well, that's O1. You do the calculation once, you put it into memory. And returning the total, that's O1. So we have 4 operations that run one time, put their result into memory, and then they stop. So then we can take all of these and we can add them together. And so that we could say the big O notation for this little script here is O4. 4 steps. We identified each step. We identified their complexity. Each one of them is 1 because it does it once, puts it into memory, and we're good. And we see O4 here, and we see that complexity is relatively low, and we see the results here as we, pressed our run button and got the answer really quickly, right? Big O4. And regardless of what numbers we use here, whether we use 2 and 4, or whether we use 1,236,546 and 236,589, regardless of the numbers that we use, it's going to complete that calculation in the exact same speed because of the complexity of our program. You saw it spit out there 1,473,135 incredibly quickly. So we've got big O kind of boiled down to the most crucial elements here, the highest order terms. So as we're dealing with something in constant time, like this is, that's going to be O to the 1. We talked about O to the N. O to the N is linear time. And that's when we get into sort of this algebraic thing. Like when we don't know how many times exactly something's going to be done. So typically when we're dealing with lists, we'll use this. We say O-N. And if we have to iterate through that list several times, that's however many times N. Right? So let's just do this again and let's kind of break through. And what could we do here? Let's make ourselves a Let's make ourselves a little list, right? And we'll do it inside of our num1 here. And we'll just make a list called L. We'll set it equal to 1, 2, 3, 4, or 5 is good enough. We'll change this up just a little bit. We'll run a for I in range 0, len L. Total is going to be num1 plus num2 plus L index I. Right, then we can call our function. So def, or add rather, 2, 3. 3. Right, so now we can kind of do the same thing again, and we can identify our different elements. And a lot of these are going to be the same. Right, but we can look at kind of what we're doing here and break things down. So we're looking up num1 still, right? So that's going to be O1, because that's one operation. To look up num2, that's going to be one operation, O1. And for the sake of argument here, we're going to say that this list that we have present here can change. Right now, it's only 4 elements long, but it could be many. And we're running this. We're running these operations one time for every operation that's in our list. Right, so that's n. So we're going to represent our n as, or our list as an n. But we're running 1, 2 operations inside of that n. So this is going to run n times, once for each element in our list. And we're going to run 2 operations for each element in our list. So this becomes 2 times n. So what we end up with is O2 plus 2n as our complexity. So we can see a little more complexity here, right? Where we were at O4, and technically this is a little more than O, because we have this assignment here, this lookup, so that's technically 3. Right, and there's other stuff that we can count here. The idea is that we want to kind of look at it and see what's more complex. So when we're calculating the time complexity of an algorithm, the more stuff that's there, and the more things that we have to consider, the more complex. that we're looking at, right? And like, what if we were doing something like a bubble sort, right? Which I think we looked at we might have looked at a bubble sort a while back. Let me see here. Let me pull up my bubble sort. We won't code one for you. We'll just pull up the example here of my bubble sorting algorithm. I had a huge list here when I was demonstrating this. This n number of numbers. But in our bubble sort, we see these nested loops. And this isn't going to be quite the same because we're doing one less in our second loop than we are in our first. Or no, that's the same. Yeah. So this is the same thing, right? We're going the same amount of numbers, one less than n, right? But n can be any number, right? Because it's a variable on its own. So when we're looking at just the bubble sort here outside of other things, for just this bubble sort where we have this nested for loop inside of this other for loop that's covering all of these numbers here, we can represent that as O n, and we're going through n, the entirety of n twice, right? So we're going through n times because we're doing it one time for each of the numbers in n. So we're going through n squared. And we call this quadratic time, and it's even higher in complexity than the other stuff that we do. But then we still have conditional statements in here, and we still have other statements in here that add to the complexity. So the O(n) squared is just for the two for loop operations that we have here. And so as you're probably seeing here, like, this is sort of difficult, right? So that's why I kind of put this as its own thing, and I have you go out and research and do things on your own here, just because I want you to kind of spend time with it and wrap your head around it. We can look at some other slides here that give us some more tips and tricks and information. Things like if we're dealing with conditionals, when we're dealing with a conditional, we're looking at whether block 1 will execute or block 2 will execute. And remember that we're looking for the worst case scenario. So if only one of these two conditions is going to execute, we're going to add up the n value, or the O value, big O value, and use the one that belongs to the larger condition block, whether that's the if block, an elif block, or an else block. Right? So like we say here, block 1, if our if condition takes O to the 1, like if it's just one constant time operation, and our block 2 is O(n), this one linear time operation. Well, O(n) is more complex than O(1), so it is the worst case scenario. And so when we calculate our big O value for this conditional statement, it's going to be O(n). With our for loops, we've already kind of talked about them. That's O(n). If a loop is going to execute n number of times, so the sequence of statements also executes n number of times. So if we assume the statements are O(1) and the time loop is n number of times, that's kind of what we looked at just a minute ago when we looked at that previous example with the add, right? If I'm looping through my array n times, and I do that twice, that's going to be O plus 1, O plus, and I have two operations in that loop. That's O plus 1, O plus 1, that's O2 times n times. So if it's just one constant time operation inside of your loop, then you can say 1 times n, which is On overall. But if it's 2 or more, you have to go with how many operations are in your loop. So if there were 2 operations in the loop, we'd do like what we said a minute ago and say 2 times n, because there are 2 operations being conducted every time, every n times that you're, all of the n times that your loop runs. And we can look at that in the same way for our nested loops. We talked about our nested loops there. That's our n squared. If we're running, we have, and that's really going to work the same way. We have those nested loops like our bubble sort that we looked at just a minute ago. We're running n loops n times, so that's going to be n squared. But you're also going to have that sequence of statements in there that's going to add to it. So we can even go back to our bubble sort and do some more calculations there to get that a little bit more fully fleshed out. Right, so let's head back to our REPL here and look at that. And we can break this down, and we can break it down line by line. So for I in range, whatever this turns out to be, that's going to be O n. And for j in range, whatever that turns out to be, that's also going to be O n. Now, since this is nested, we combine these, and we have O n squared. And so in each of these, so now we have a conditional here. There's no else that goes along with it, which would mean that else would be our least complex situation. So since we go for the most complex scenario, we have 1, 2 different variable assignments here. I just wrote them in a bit of a different way. So each time it goes through n operations, in our J array, it's doing them 2 times. So that's like what, 2n plus n squared, something like that. So we get this high-end complexity here. And so the last thing that we want to examine is function invocation. When a statement involves a function or procedure invocation, so when you're invoking a function inside of another function, right? the complexity of the statement includes the full complexity of that other function. So if, for example, you're running a loop that executes another function X amount of times, the complexity in that other function is going to be multiplied by that situation. So it's not just, we're not just counting lines here, we're counting operations. And so when you're counting operations, you have to go to that other function and count the operations in it. And so like I said here, this is a big, heavy, complex scenario. And that's why we kind of put this as its own thing and left it as something that you can research and learn and wrap your head around with this. So this is actually where I'm going to stop. And you might feel just as confused, or maybe even a little more so confused, about algorithmic complexity now as you did when you started the video, about 40 minutes ago. So this is the encouragement to kind of go out and do your own research and look into these things in order to foster yourself a better understanding of Big O notation, complete the assignments for the module, and start striving toward more efficient programming. But this is where I'm going to leave you for today. I want to thank you for watching. I want to thank you for watching all semester long. And I'll hang out in the chat for just a couple minutes, just in case anybody here with me has any questions. If you're watching this later and you have some questions, please let me know. But as always, thank you for watching. And we'll see you next time, whenever next time may be.